Okay, so welcome to 7.2, which is the golden ratio. The golden ratio. And the Fibonacci sequence. Fibonacci sequence. Okay, so let's note that if I take the square root of any number a and I square it, I just get a, provided a is greater than or equal to 0. Because, yeah. So let's consider the following in what's called rationalization. So let's say I have 1 divided by the square root of a minus the square root of b, where a and b are numbers greater than 0. Well, this is equal to itself, of course. Let me draw that a bit better. So I can multiply this by 1, and it won't change anything, because anything multiplied by 1 is just itself. Only in this instance, that 1, I'm going to make that a very specific 1. So we have 1 over the square root of a minus the square root of b. And what I'm going to do is I'm going to make that 1 what's termed the conjugate of what's on the bottom here. So anything divided by himself is 1. So I'm going to say, how about the square root of a plus the square root of b divided by the square root of a plus the square root of b. I'm allowed to do that as long as whatever I'm multiplying by is the same as 1. Okay, so now what this means is I can multiply the two numerators. So I have 1 times the numerator, the square root of a, plus the square root of b, divided by, now I multiply the two denominators. So I'll have in parentheses the square root of a minus the square root of b times the quantity, the square root of a plus the square root of b. Okay, so what does that give us? Well, in the numerator, we just get 1 times anything as itself. So the numerator is just the square root of a plus the square root of b. But the denominator, let's FOIL. So we take firsts, the two first terms. So that would be the square root of a times the square root of a, which is the square root of a quantity squared. Then I look at the outers. It'll be plus the square root of a times the square root of b. Then let's look at the inners. It'll be minus the square root of a times the square root of b. Now let's look at lasts. It'll be minus the square root of b times the square root of b, which is the square root of b quantity squared. Okay. So what do we have here? We have that plus square root of a, square root of b, and minus square root of a, square root of b goes away. So in the numerator, we still have the square root of a plus the square root of b. But now in the denominator, we have the square root of a squared, which as we saw above is just a, minus the square root of b squared is also just what it is, b. Okay, so we have that 1 over the square root of a minus the square root of b is equivalent to the square root of a plus the square root of b, all divided by a minus b. So let's go ahead and put a box around this. Oh, well, no, okay, tried. Let me try again. There we go. Okay, so hopefully that makes sense. Let me move that down maybe one line. Let's see, down there. Does that look okay? Okay. So creating the golden rectangle. So creating a golden rectangle. Golden rectangle. So number 1 is to create a square with side length 1. So create a square, and I'll show all of this after I write these down, of side length 1, side length 1, length 1. So step number 2 is divide the bottom side in half. So divide the bottom side in half. Bottom side in half. So step 3 is to draw a line from the point in step 2 to the right top corner. So draw a line. From step 2 to the top right corner. Top right corner. This will make more sense once I draw it out. And number 4. Use the length of number 3, step 3, as the radius of a circle. Radius of a circle, which we extend to which we intersect with an extension. Of the base. Okay. Number 5, the point of intersection. In step 4. Has length of phi, the golden ratio. Golden ratio. So what does this mean? Ratio. So I'm going to start in purple with a square of side length 1. So let's do 4 as my length 1. Pardon me, maybe 5. Maybe I can make this a bit bigger. Or 6, let's see. 2, 3, 4, 5, 6. So that's my length 1 for this guy. 1, 2, 3, 4, 5, 6. So assume that this has length 1. This has length 1. These are terrible ones. I'll just put the straight up and down ones. So step 2 was to divide the bottom in half. Okay, so now I know that this is 1/2 to here. Step 3 is to draw a line from that point to the top right corner. Okay. Step 4 is to have that length be a radius of a circle, which I'm going to extend down to an extension of the base. Okay. The point where these intersect has length phi, which means the golden ratio is the length from this point of intersection to the edge of the square. So that is the golden ratio. But we need to find out what the length of that is. So let's note. So note, we can use the Pythagorean theorem. We know that the height is 1. This is a right triangle here. And I know that the base here of this triangle is 1/2, right? So I have that phi, which I did, phi squared, no, phi, how about this? Not phi, what am I saying? The hypotenuse. So let's call that hypotenuse h. I know that h squared is equal to 1/2 squared plus 1 squared using the Pythagorean theorem. So I have that h squared is 1/4, because 1 times 1 is 1 and 2 times 2 is 4. And of course 1 is just 1, but I want a common denominator, so I'm going to write 1 as 4/4. So I have that h squared is 5/4. Actually, let me just write 5/4. You guys can see that that's true. 5/4. So therefore h is the square root of 5 over the square root of 4. But the square root of 4, of course, is 2. So what that means is this length here is the square root of 5 all over 2. This is the radius of that circle, that green length. Okay, so what is phi then? Well, phi is going to be 1/2 plus that hypotenuse there, that square root of 5 all over 2. So the way we can write phi is simply 1 plus the square root of 5 all over 2. And that is the golden ratio. Okay. So now theorem. So the golden rectangle satisfies. So the golden rectangle, which we just kind of drew. So the golden rectangle satisfies that. The ratio of the long side to the short side. So the ratio of the long side to the short side, in each rectangle, and what do I mean by that? You'll see in a moment, is equal or is equivalent. Okay, so let's go ahead and draw another golden rectangle. So this time let me draw the just do it of length 4. Yeah, maybe I'll do length 6 just to keep it the same. Okay, so here's my rectangle of length 1, right? But then I extend it out. Actually, do you know what? No, I want to make it smaller. This is way too big. Let's just do a smaller one. No, it seems silly, but just... Okay, so now let's say that I extend it out to about here using the process that I had before. So I have that the bottom length is phi. We do phi in orange. So I've got the golden rectangle that I created above. So this is length 1 here, this is length 1 here. So what is that small little length going to be then here? And this length is phi minus 1. Actually, let me explicitly show it. It's a whole length. The whole top would be phi, but I'm subtracting 1. So it's phi minus the 1 on the left, right? So this little portion here is phi minus 1. So what we're saying is that the large rectangle, long side to short side. So what I want to do is long side to short side. So how should I do this? So let's look at the larger rectangle, which would be this. So long side, long over short in the larger rectangle is going to be the golden ratio phi over the short side 1. But now let's look at the smaller rectangle, which is this one right here, the small little one on the right. So now let's do long side to short side. And the long side in that rectangle, of course, has length 1. Actually, let me color code it. The length is 1. And now the short side is phi minus 1. Phi minus 1. So what this theorem is saying is these two are equal. So, for example, let's show that. Phi over 1 is equivalent to 1 over phi minus 1. Okay, and let's recall before we move on. What was the value for phi? Not that it matters, but phi was 1 plus the square root of 5 all over 2 was equal to, not plus. What am I saying? Okay, so let's note, what is phi minus 1? Maybe I can simplify that before I look at the fraction. So phi minus 1, what's in the denominator there, will be 1 plus the square root of 5. Actually, let me color code it. Let's call phi orange. So phi is 1 plus the square root of 5 all over 2, and I'm going to subtract 1. But 1 is the same as 2 over 2. So now this is going to be a square root of 5 minus 1, because 1 minus 2 is a negative 1, all over 2. Okay, so there we are. So that's what phi minus 1 is, in effect. Okay, so phi minus 1, so I'm going to use that in my denominator. Phi minus 1. Okay, so now let's get started. So, consider the fact, well, I probably shouldn't have used that color. So consider, if I have that phi minus 1 is equal to the square root of 5 minus 1 all over 2, minus 1 all over 2. Then this implies that the reciprocal's 1 over phi minus 1. I just flip everything upside down. Will be 2 divided by the square root of 5 minus 1. Just flipping both fractions upside down. Okay, so now let's get started with the proof, finally. So I need to show that phi over 1, phi divided by 1 is equal to 1 divided by phi minus 1. Okay, so I have the square root of 5 plus 1 all over 2, or let me write it the formal way, 1 plus the square root of 5, 1 plus the square root of 5 all over 2. Is that equal to? Okay, well, 2 divided by the square root of 5 minus 1, is that the same thing? Question mark. Well, let's do the rationalization thing again. I'm going to multiply this through by a very specific 1. So what do I get? So I have 2 divided by the square root of 5 minus 1. And so my trick is to multiply by the 1 that is the same as a denominator except with a positive sign. So I'm going to take the denominator, the square root of 5, and I'm going to add 1. So I need to do that top and bottom because I'm multiplying by 1. So anything divided by himself is 1. Okay. So what do I get then? Let's see. Let's multiply the top. I get 2 times the quantity, the square root of 5 plus 1, divided by multiplying the 2 guys on the bottom. So let's go ahead and FOIL that out. And that turns out to be first guy squared, so the square root of 5 squared. Then the outers will give me plus the square root of 5. The inners will give me minus the square root of 5. And then the lasts will give me minus 1 squared. Okay, so that's FOILing that out. Okay, so I know that the square root of 5 goes away. So let's distribute in the numerator. So what do we get? In blue, the numerator becomes 2 times the square root. Actually, do you know what? Let me not distribute because I see what's coming. I see something interesting. So I'm just going to keep this right now as 2 times the square root of 5 plus 1. But now what happens in the denominator, and it doesn't matter if you distributed because you would have undone it, we're going to get 5 minus 1. And 5 minus 1 is 4. And 2 over 4 can reduce. So this will be 2 times the square root of 5 plus 1 all over 4. And of course, 2 goes into 4 twice. So look at that. Look what we get. In the end, we get the square root of 5. Actually, let me keep the colors the same. We get the square root of 5 plus 1 all over 2, which is exactly the same as the left-hand side, right? 1 plus the square root of 5 all over 2, tomato, tomato. Okay, so we have proven that theorem. Okay, so definition. So the Fibonacci sequence, that's what we're defining. The Fibonacci sequence. Fibonacci sequence. So it is defined recursively. It's defined recursively by the nth Fibonacci number will be the nth minus first, that is a previous Fibonacci number, plus the f sub n minus second, the second previous Fibonacci number, where f sub 0 is 1 and f sub 1 is 1. So for example, so find the first 8 terms of the Fibonacci sequence. So find the first 8 terms. 8 terms of the Fibonacci sequence. Fibonacci sequence. Okay, so we know, what do we know? We know that f sub 0 is 1. We know that, what color should I use? F sub 1 is also 1. So we're just starting with f sub 2. So f sub 2 is going to be, what color? F sub 2 minus 1 plus f sub 2 minus 2, according to the rule. So that is going to be f sub 1 plus f sub 0, because 2 minus 2 is 0. Okay, well, we had those given initially. F sub 1 is 1, and f sub 0 is 1 as well. So the second Fibonacci number, which is actually third, is 2. Okay, so moving on. Let's do this color. So now what is the third Fibonacci number? Well, that will be f sub 3 minus 1 plus f sub 3 minus 2. So what does that give us? That gives us f sub 2, the second Fibonacci number, plus f sub 1, the first Fibonacci number. So we found that f sub 2 was 2, and we're going to add to that f sub 1, which was 1. So the third Fibonacci number is 3. So is the fourth Fibonacci number going to be 4? Let's find out. So let's say we have f sub 4. I claim that that's going to be f sub 4 minus 1 plus f sub 4 minus 2. So that's going to be f sub 3 plus f sub 2. Okay. Well, we found that f sub 3 was 3 plus we found that f sub 2 was 2. So look what happens. 3 plus 2 is not 4. It's actually 5. Okay. Oh, did I use the wrong color blue? Okay, I'll just change this to that color blue. Okay, so now let's do f sub 5, which is going to be it's going to be f sub 5 minus 1 plus f sub 5 minus 2. So that's going to be f sub 4 plus f sub 3. And we found that f sub 4 was 5 and f sub 3 was 3 So 5 plus 3 is 8. So f sub 5 is 8. Okay, so now let's do f sub 6, which is going to be f sub 6 minus 1 plus f sub 6 minus 2, which of course is f sub 5 plus f sub 4. And we found f sub 5 was 8, and f sub 4 was 5, so 8 and 5 is 13. So now, boy, I've already used that color, but that's okay. So f sub 7 will be it's going to be f sub 7 minus 1, which is f sub 6, which we found to be 13, plus f sub 7 minus 2, which is f sub 5, which we found to be 8. Okay, so what is 8 and 13? That's 21. Okay, so finally f sub 8. Okay, so that's going to be f sub 8 minus 1, which of course is f sub 7, which we found to be 21, to which we're adding f sub 8 minus 2, which is f sub 6, which we found to be 13. So 13 and 21 is 34. Okay, so the first 8 terms, so the first, well, technically 9, but few terms of the Fibonacci sequence, which goes on forever. The Fibonacci, 1 and 2 C's, Fibonacci sequence. It's R. Well, we have 1 and 1, which were 0. Then we got 2, 3, 5, 8. 2, 3, 5, 8. Then 13, 21, and 34. 13, 21, and 34. But this sequence can go on forever. So we say ... So note, basically each term in the Fibonacci sequence is the sum of the previous 2 terms. So each term in the Fibonacci sequence is the sum of the 2 previous terms. The sum of the 2 previous terms. Right, so 34 is 21 plus 13. We have that 21 is 8 plus 13. We have that 8 is 3 plus 5. We have that 5 is 2 plus 3. So I just take the 2 previous values and add them together. So let's consider, hopefully I can fit this on one page, because this is it for this section. So let's consider, let me color code this. So the first f sub 1, Fibonacci number 1, divided by Fibonacci number 0. Okay, so what do we get? We get 1 over 1, right? They were both 1. And that, of course, is 1. Now let's do f sub 2. What color did I use for f sub 2? I used hot pink. Okay, so let's have the ratio, what is f sub 2 divided by f sub 1? Well, that's going to be now 2 over 1, which is 2. Right, 2 over 1. Now let's do f sub 3 divided by f sub 2. So that's going to be f sub 3 we found to be 3 divided by 2. 3 over 2 is 1.5. Okay, now let's do f sub 4. What color did I have for f sub 4? I had blue. Okay, so f sub 4 was blue, and I'm going to divide that by f sub 3. So what do we get? No, f sub 3 is 3. F sub 4, however, turned out to be 5, right? So 3 goes into 5 once, with 2 out of 3 left over. Okay, so 2/3 is 0.6 bar. That's 1.6 bar. You can use your calculator, of course. Now let's do f sub 5 divided by f sub 3. Sorry, f sub 4, rather. Counting, not my strong suit. Okay, so what do we get? So f sub 5 was 8. So 8 over 5. So do you agree that 5 goes in to 8 once, but 3 over 5 left over, which is 6 over 10. So that's 0.6. So I get 1.6 as the ratio there. Now let's go up here. I believe, yeah, f sub 6 was in yellow. So f sub 6 divided by f sub 5. F sub 5. So f sub 6 was 13 divided by 8, and I won't make you do this in your head. Just use a calculator. So 13 over 8 is 1.625. Okay, so now let's do f sub 7, which was in orange. So f sub 7 divided by f sub 6. This is going to be 13 in the bottom, 21 on top. So 21 over 13 is 1.615. Now let's do f sub 8 divided by f sub 7. So you have now 21 on the bottom and 34 on the top. Okay, so put that in your calculator. And what you should get is 1.619. 1.619. And if you plug in phi, which is 1 plus the square root of 5 all over 2, what you get is something approximately equal to 1.619-ish. So as n increases, f sub n divided by f sub n minus 1 approaches phi. So the ratio of Fibonacci numbers approaches phi the larger n gets. Okay, I hope that makes sense, and I'll see you in the next section.